Welcome to iTTV for Form 5 Physics. Today, the title of the lesson is Waves. In this lesson, we're going to start with the first chapter of Form 5 Physics, which is called Waves. Now, we all know that a wave, if someone is leaving, is something like this, where you're waving to somebody. Now, in truth, a wave is very similar to this action. A wave is a repeating action, or an action that basically will move to and fro. When I wave my hand, I'm moving to, fro, repeating itself all the time. In general, waves are created by some kind of vibration. The vibration will set the system off into an oscillation. This oscillation, which will be a repeating oscillation, will create our wave for us. Now, this word oscillation, please don't be afraid of it. All this word means is that we have a repeating action. Let's start by having a look at some of the key words and their meanings for this lesson. What are waves? Wave is a transfer of energy without transferring matter. Transfer of energy by matter. In the diagram, you see a boy throwing a stone at a window. In this case, energy is transferred from the source, the boy, to a receiver, the glass window, with the transfer of matter. So in this case, we are transferring energy, true, but the energy is being transferred along with the stone, meaning that we are transferring both energy and matter at the same time. But in the case of a wave, we are only transferring energy from the source to its final destination. There is no transfer of matter. Now look, let's try and demonstrate this here using this water. Now, what I'm going to do is, I'm going to put this piece of paper in the water. Now, I'm going to create some water waves using the dropper. What I hope you notice is, as the water waves that I create move past the paper in general will not move with the wave, but instead oscillate up and down, which is, they are not moving with the wave, which means I'm trying to get you to understand that the matter is not being transferred, just the energy is being transferred. Let's have a look and see whether you can see this. So I'm going to create my wave by dropping the water in here, and you notice that really the paper is not moving as the wave goes by it. The paper stays almost stationary, which means that as the wave goes past the paper is just maybe possibly moving up and down as the wave goes by, but it's not moving over to the edge of the tray because matter is not transferred. So remember, with a wave, energy is transferred, but matter is not transferred. Evidence 1. Vibration in water creates water waves. The wave is transferring energy without transferring matter. Example 1. Any object that vibrates on the water surface will produce water wave. Example 2. A string under tension that vibrates will produce sound wave. So any type of vibration will produce a wave. Evidence 2. Air molecules do not move to the candle flame, but the candle flame is moving back and forth. Note, air molecules will be vibrating at the same place. So with the candle flame, what we're having here is sound waves. As the sound is moving back and forth, and it goes past the candle flame, it causes the candle flame to move left and then right, left and then right. And this movement that is being created is because the wave is passing past the candle flame. But the candle flame itself does not move. Neither does the candle move as the wave goes by it. It just oscillates in one position. So when a wave passes a point or passes some sort of material or matter, that matter is going to move. Yes, it will move. It will move in the direction that the wave is going to dictate. Either it will move up and down, in which case we have a transverse wave, or it will move left and right, in which case we have a longitudinal wave. But it moves in one area. It does not move along with the wave. So please understand this first thing about waves. Waves transfer energy, but waves do not transfer matter. Wavelength. The distance between a point on one wave and the same point on the next wave. It is often easiest to measure this from the crest of one wave to the crest of the next wave. But it doesn't matter where, as long as it is the same point in each wave. So, what are we talking about now? I can see you at home going, wavelength? Crest? What is he talking about? Well, let's go up to the board and have a look and try and work out what it is I was actually trying to get you to understand. We have a general description for a wave. Let's sketch this on the board. So most waves are drawn using a graph. So we've got a graph like this with our x and y axis, like so. On this graph, we draw our wave, which usually looks like a curve going up and down. So let's sketch this curve in. Like so. Now, with this graph, we've got particular things that we need to identify. So let's identify all of these main bits now. The top of a wave, up here, we call this the crest. The lower part of a wave, over here, we call this the trough, like so. Now there are other key parts to a wave that we need to understand. This point here, which I'll mark with a 0, represents our equilibrium, our point of origin. The maximum displacement from our point of origin, which means from here all the way up to here, this represents A. A is our amplitude. The amplitude is the maximum displacement from your point of origin. It is only from the origin line here to the top of the wave. It is not the distance from the top of the wave to the bottom of a wave. So A is our amplitude, which is, like I said, the maximum displacement. The amplitude is very much linked to the amount of energy that is in the wave. The greater or the bigger the amplitude, the greater the amount of energy in a wave. Let's put that out on the board. So point 1, amplitude. Amplitude. This, firstly, is the maximum displacement. Number 2, it basically is linked to your energy. Like I said, if your amplitude is bigger, your energy is greater. So let's make that point number 1 that we need to remember. You need to remember this throughout the chapter on waves. Any reference to amplitude increasing or amplitude decreasing is directly related to energy. So that's number 1. Number 2, we want to have a look at this concept of wavelength. The wavelength is the distance from one particular point in the wave to the next consecutive point that is similar. Now, using this wave here, let's say that I begin over here. if I start here, the next similar point to this, going up, coming down, would be here. So the distance from here to here would represent one wavelength. Let's say I start from the top here. The distance from here to the next similar point, which will be up here, well then that represents one wavelength. So if this is one wavelength, we have a symbol that we use to represent a wavelength. The symbol is lambda, like that. So remember, a wavelength is the distance from one point to the next consecutive point that is similar. Next, with the same wave, we want to have a look at what is known as the period. The period is the time it takes for one complete wave, or as we say, one complete cycle. Now, if I start from here, the time it takes to go up, down, and back to this point here, that represents T. Capital T is the period, the time for one complete cycle. Let's put that down on the board as well. So T, this is my period, and it is the time for one complete cycle. Okay, so let's box that up as well. Also quite an important thing, because we use this to calculate frequency. Frequency, which is the next thing that we need to understand. The frequency is the number of waves you have within 1 second. If, for instance, you have 10 waves in 1 second, then your frequency is 10 Hertz. The unit for frequency is Hertz. The short form is Hz, capital H, small z. If you have 2 waves in 1 second, then what you have is a frequency of 2 Hertz. If you have 100 waves in 1 second, what would your frequency be? Correct, it would be 100 Hertz. Let's try on the other side of the scale. If you had 1/4 of a wave in 1 second, what would your frequency be? It would be 0.25 Hertz. Correct. So now that we understand the key things, amplitude, wavelength, the top of a wave is called a crest, the bottom of a wave is called a trough, the time for one complete cycle is known as the period, and the number of waves in 1 second represents your frequency. So these 4 are the key things that you need to remember for a wave. Amplitude. The height of the wave is called its amplitude. The amplitude of a wave is its maximum disturbance from its equilibrium position. Amplitude is not the distance between the top and bottom of a wave. Amplitude relates to loudness in sound and brightness in light. Frequency. The frequency of a wave is the number of waves produced by a source per unit time. It is the number of waves that pass a certain point each second. The unit of frequency is the Hertz, Hz. It is common for kilohertz, megahertz, and gigahertz to be used. For example, most people cannot hear a high-pitched sound above 20 kilohertz. Radio stations broadcast radio waves with frequencies of about 100 megahertz. Most wireless computer networks operate at 2.4 gigahertz. Period. The period of a wave is the time taken for one complete cycle. It is measured in seconds. Frequency is related to the period. F equals 1 over t. So we can calculate the frequency if we know what the period is. Let's have a quick example of this. Let's say that we have a wave. Let's say that here I have a wave that goes up and down, and the time it takes for this wave is, let's say, 2 seconds. So my period equals 2 seconds. From here I can calculate the frequency. Frequency equals 1 over t. So F equals 1 over t, which is 1 over 2. So I have a frequency of 0.5 Hertz, like so. So if you know what the period is, you can calculate the frequency. And it's very common in examinations for them to give you the period, because what they really want is for you to calculate the frequency. So they give you the period, you calculate the frequency. Be aware of this. Wave speed. The wave speed of a wave is the movement of how fast a crest is moving from a fixed point. For example, the speed of sound wave is about 330 meters per second. The speed of light is 2.99 times 10 to the power 8 meters per second. If the wavelength of the wave is lambda, the wave moves forward a distance of f times lambda per second. Therefore, the speed of waves can be represented by the formula V equals f lambda. So this is the formula for wave speed. V equals f lambda. You need to remember this because it's a common equation in examinations. But the most important part of this equation is really the relationship between the frequency and the wavelength. Based on what we have studied before, if you look at the equation, you will understand that frequency and lambda are inversely proportional. Meaning, if the frequency increases, the wavelength will decrease. Let's put this down on the board, because this is possibly the most important relationship in the whole chapter. So, what we get is, when the frequency increases, the wavelength decreases. When f goes up, lambda comes down. Or inversely, or vice versa is what I mean. If lambda goes up, frequency will come down. So this is the most important of all the relationships, because we use it all the time. If the wavelength of a sound increases, what happens to its frequency? Well, the frequency will decrease. If you have high frequency radio signals, what can you tell me about the wavelength? Well, if the frequency is high, the wavelength must be short. So this is the most, like I said, important relationship that you need to remember for this entire chapter. It keeps coming back out over and over again. Now, the next really important thing that we need to understand is how to describe oscillatory motion. We have two general oscillatory motions that come out in exam papers. One is the swinging of a pendulum. As the pendulum swings back and forth, we tend to be asked questions such as, which one represents a wavelength? Or can you sketch a graph to represent the movement of the pendulum? Another one that we commonly get is a weight on a spring. As the spring bounces up and down, or contracts and compresses and extends, and the weight moves up and down, once again we are asked to draw the graph or to describe or identify what would be a wavelength, or what is the period, or what is the frequency. So let's have a look at these two on the board in just a bit of detail so that we understand what it is we are really wanting to do. So number one is the pendulum. Now understand that with a pendulum, over here, right in the middle, this is our point of origin. As the pendulum starts to swing, I'll just put an O there for origin. As the pendulum starts to swing over here, and then back, up here, and then back here, it will do one complete cycle. Remember, for one complete cycle, you have to go through all the points and then return to your origin. So if I start a pendulum here, or if I say I start the pendulum up here, which makes a bit more sense. I take the pendulum up here, I let it go, the pendulum swings back to its origin, then it keeps swinging up to here, and then it swings back and goes back to this point. That will represent one full cycle of the pendulum oscillation. Now, if you were going to sketch that, so let's imagine now sketching this on a graph. You see, this is where it gets a bit tricky. You've got to understand that your origin is here, and you were starting over here, which means you're not starting at the origin. You were starting up here. As you let it go, the wave comes back to its origin at this point, then moves across to this point, which will represent the trough. Then from the trough, it goes back to its origin, like so, and then back up to where it started, like so. This is one lambda, one full cycle. So you need to imagine where you are starting. It's very similar with a spring and a weight. It's the same thing. To start the spring-weight system in oscillation, you need to pull the spring down. Let's draw this up here, yeah? So you imagine you've got a spring and you've got a weight underneath the spring. Now, to start this system moving up and down, I need to either pull it up, compress, and let it go, or pull it down, extend it, and let it go. Once it starts to oscillate, it goes up and down. Remember, one lambda will be from here up to here, and then back down to here again. So let's do that again. If we start here, it's got to go from here up to here, and then back down to here again. You need to come back to where you started to create that one full cycle. So just be aware of these two systems, because we commonly use them in examination questions or in general to make you understand about oscillation, what one cycle is, and how to calculate period and frequency from real life situations. Now let's move on and do a few questions. In the diagram above, what is the wavelength of this wave, and what is the amplitude of the wave? So you've got a wave drawn on some graph paper. Let's assume that the graph paper boxes are about 1 centimeter. So let's calculate the wavelength. For this case, let's try and work the wavelength out from crest to crest. Now, if you remember up here, what we did was, we said that the wavelength was from the top of the crest to the next crest. Now, if you look at the question, can you work out how many, approximately, how many 1 centimeter boxes is the distance from this crest to this crest? Have you done it? The next question was, what is the amplitude? Using the same idea, can you work out roughly what this length is in the diagram that you have? Have you done it? Let's have a look at the answers. The answer is, the wavelength is 3 cm. So it's approximately 3 centimeters from crest to crest. And the amplitude was 1 cm. Let's try another question. Which two letters represent the wavelength? Now you have more than one wavelength represented in this diagram. Please remember, it's from the same point to the next repeating point. Try and work out how many waves or wavelengths you have in this diagram. Have you done it? Let's have a look at the answer. The answer is, we have three possibilities. From B to F, which is crest to crest. From A to E, which is from point of origin to the next point of origin. Or from C to G, which is from the half cycle point to the next half cycle point. Let's try one more. If a wave has a wavelength of 5 meters and a period of 2 seconds, calculate the frequency and the wave speed. So we want to calculate two things here, frequency and wave speed. Now, in order to calculate the frequency, we need to return to this formula over here. F equals 1 over T. The question says that the period was 2 seconds, which is pretty much the same calculation you have here. So if F is 1 over T, this means the frequency is 1 over 2, so your frequency will be 0.5 Hertz. Good. Now we need to calculate the wave speed. In order to calculate the wave speed, we're going to use the formula. Let's write it over here. V equals F lambda. Now, we've said that the wavelength is 5. Let's extract our information. The wavelength is 5 and the frequency we've calculated was 0.5. So if you multiply these two numbers, what are you going to get? Try it. Firstly, the frequency 0.5 Hertz. And finally, the wave speed 2.5 meters per second. So let's summarize what we've done. Remember the first thing. A wave transfers energy from one place to another place without transferring matter. We have two types of waves, which I mentioned earlier, a transverse and a longitudinal wave, which we'll look at a later lesson in more detail. But a wave in general is represented by a curve such as this. From a curve like this on a graph, we can find out the amplitude. Remember, the amplitude is related to energy. More amplitude, more energy. We also know what is a wavelength, which is from one point to the next repeating point. We also know that the time taken for one complete cycle is known as the period. And the number of waves that we get in 1 second is called the frequency. We can calculate the frequency using a formula F equals 1 over T. And we can calculate the speed of a wave, or wave speed, using this formula over here, which is V equals F lambda. So these are the key things that we need to remember for our formulas. And for the main topics, or the main, what should I say, the main points about a wave in general. Transfer of energy, amplitude, wavelength, period, frequency, and wave speed. These are the main things you need to understand. But the most important thing is you need to remember the relationship between lambda and frequency. Remember, they are inversely proportional. When the frequency increases, the wavelength decreases, or vice versa. It's going to keep coming back over and over again as we go through this chapter. So please always be aware of that key relationship. That's all the time we have for this lesson. Thank you for watching iTTV.